지난주에, 지난 시간에 이제 failure mode하고 failure mechanism에 대해서 배웠죠. 그래서 failure mechanism은 근본적인 이유가 되는 거고, failure mode는 우리가 관찰할 수 있는 거, 보이는 게 되겠습니다. 이번 시간에는 FMAC라는 방법에 대해서 배우고, 금요일 날은 FMAC로 직접 그 시스템을 분석해보는 방법을 배우겠습니다. 그래서 요즘 해양플랜트에 대해서 많은 이제 우리나라 특히 이제 중소업체들이 이제 기자재 업체들이죠. 기자재 업체들이 해양플랜트를 이제 기자재를 납품해 보려고 그럽니다. 근데 이제 부끄럽게도 우리나라의 해양 플랜트의 이제 기자재 국산화율이 거의 0%입니다. 그러니까 이제 배관이나 이제 벌크 머티리얼이라고 그러죠. 그럼 이제 배관이나 이제 그런 거 빼고 펌프, 컴프레서, 인스트루먼트, 전개장 그런 쪽에는 우리나라 제품이 거의 못 들어갑니다. 근데 그게 이제 가장 큰 이유 중에 하나가 우리 제품이 얼마나 안전하고 신뢰성이 있는지를 체계적으로 보여주는 그 다큐멘테이션이 돼야 되는데 다큐멘테이션이 안 됩니다. 그래서 똑같은 제품을 납품하더라도 배에다가 납품하면은 이렇게 되게 데이터 시트, 스펙 시트 이제 두세 장이면 되는 일을 해양 플랜트에서는 이제 이런 바인더로 3개, 4개를 내야 됩니다. 우리 시스템이 얼마나 안전하고 믿을만하다 이런 것을 증명을 해서 내게 되겠습니다. 그런 게 잘 안 되는 게 되겠는데 거기에 가장 기본적인 도큐먼트가 FMAC가 되겠습니다. 우리 제품은 고장 나면은 어떻게 그 고장들이 연결되어 있고 그게 얼마만큼 디텍트하기 쉽고 고치기 쉽다, 어렵다 이런 것들 체계적으로 분석한 게 되겠습니다. FMACA. 그래서 방법론은 아주 간단합니다. 근데 이제 대부분의 우리나라 이제 기자재 업체들이 이런 측면에서 익숙하지 않기 때문에 심지어 대형 조선소도 익숙하지 않습니다. 이런 방법에 대해서 익숙하지 않기 때문에 이제 그게 이제 한 걸림돌이 되겠습니다. 근데 이런 이제 기자재 이제 국산화율이 낮은 게 이제 해양 플랜트뿐만 아니고 이제 육상 플랜트에서도 마찬가지입니다. 우리나라가 이제 건설사까지 다 해서 1년에 100조 정도를 이제 플랜트를 수주를 한다고 그래요. 이제 그럼에도 불구하고 거기에 들어가는 이제 되게 고급 기자재는 국산화가 거의 안 되어 있습니다. 그래서 예를 들면 이제 펌프 컴프레서 같은 것도 이제 거의 이제 공기 컴프레서, 에어 컴프레서나 이제 워터 펌프 같은 것은 이제 국산화가 되어 있지만은 이제 오일 가스를 압축하는 압축기나 오일 펌프 같은 것은 아직 거의 국산화가 안 되어 있는 실정입니다. 특히 이제 전개장 부분은 더 이제 열악하죠. 그래서 failure mode effect and criticality analysis. 그래서 criticality에 괄호가 있죠. 그래서 이제 저 말을 넣어서 하는 경우도 있고 안 넣어서 하는 경우도 있게 되겠습니다. 이제 이 그림 많이 보셨죠? 이제 한 4번쯤 보셨을 거예요. 해자드 있고, 액시던트 있고, 그게 미치는 이제 임팩트 또는 컨시퀀스가 있게 되겠습니다. 그래서 해자드가 액시던트로 연결되는 이 부분이 어떻게 연결되는지를 해석하는 게 이제 causal analysis가 되겠고, 이게 사고가 나면은 그 영향들이 어떻게 전파되느냐 해석하는 게 consequence analysis가 되겠습니다. 그래서 causal analysis 중에 오늘 배울 게 FMECA가 되겠습니다. 다른 방법, fault tree analysis나 reliability block diagram은 조금만 기다리시면 됩니다. 개봉 박두. Hi, Ellen. FMEA is usually called also FMEA. Initially, the FMEA was called FMEA, failure mode and effect analysis. The C in FMEA indicates the criticality or severity of the various failure effects. And the failure effects are considered and ranked. Today, FMEA is often used as a synonym for FMEA. So you don't have to distinguish two words. Two words mean exactly the same thing. There were proposed many methods for analyzing the fault, failure mode, and effect. As you may remember, the FMEA was proposed many years ago. To the best of my memory, it was around 1950. So it is really 60 years ago. So FMEA survived the test of ages. FMEA is a methodology to identify and analyze all potential modes of the various parts of the system and the effect these failures may be on the system. How to avoid the failures or mitigate the effect of the failure on the system is the objective of the FMEA. There are many comments on the FMEA. There are pros and cons. These are Mr. Omdal is on the positive side. FMEA is a technique used to identify, prioritize, and eliminate potential failures from the system, design, or process before they reach the customer. And so FMEA is considered by many engineers that FMEA is a technique to resolve potential problems in a system before they occur. So the objective of FMEA is the first objective is identify the failure mode and analyze the effect, and the last objective is what should we do to prevent the failure mode. These are the background of FMEA. FMEA is one of the first systematic techniques for system reliability analysis. It was developed by U.S. military. It is not surprising that the defense industry was leading the system reliability in early ages of system reliability engineering. So it was developed by U.S. military. The first guideline was military procedure, MIL-P. So if you see these three alphabet, MIL, that means military standard of the United States. MIL standard P 1629, procedure for performing a failure mode, effect, and critical analysis. So it was developed around the 1950s. FMEA is the first widely used reliability analysis technique in the initial stage of product system development. FMEA is usually performed during the conceptual and initial design phase of the system. Any system reliability analysis method can be applied to the design stage, and to the operation stage or detailed design stage. But you should remember that the value of the system reliability analysis is high in the design stage. So this is the guideline how to use FMEA. FMEA can assist in selecting design alternatives. You may have several design options. So you may apply FMEA, or you can analyze all the design alternatives with FMEA. Then you can choose which is the best alternative. And FMEA ensures all conceivable failure modes and the effect on operational success of the system has been considered. So FMEA try to find out all the possible, all the conceivable failure modes, and FMEA can develop all the criteria for test planning and requirement. That means we can identify the failure mode, then we can recognize which test should be conducted to remove the failure mode. And it can provide historical documentation for future reference to aid in analysis of field failures and the consideration of design changes. That means, as I stressed at the beginning, you need full documents, several documents to have a qualification from the owner side. So FMEA can provide a good documentation, kind of initiator of the documentation. It can provide a basis for maintenance planning, where we identify the failure mode and kind of countermeasures. Countermeasures can be a design change or effective maintenance policy against the failure mode. So it can provide the baseline for maintenance policy. It can provide a basis for quantitative reliability and availability analysis. In order to analyze, quantitatively analyze the system reliability, we need to know the logical connection of component and their failure rate. So FMEA can provide the first picture of a system configuration and the component involved, and it provides some kind of first estimate of failure rate utilization. This is the basic questions FMEA try to answer. First is how can each part conceivably fail? How an item or component fail? This is the first question FMEA should answer. Second is what mechanism might produce this mode of failure. In short, failure mechanism. We try to understand, try to find out the failure mechanism of the failure mode. Third, what could be the effect if the failure did occur? That means we try to guess the effect of the failure. Next is the failure in the safe or unsafe direction. That means we consider the outcomes of the failure. So then we can know that if the failure is safe or unsafe. Next question is, how is the failure detected? So There are many detection methods. One is detection by operators, noise or vibrations or the color change. But as you know, these days the instrument, electric or electronic instruments are well developed. So we can put some sensors to detect the failure. For example, temperature measurement or thermocouples, pressure measurement or pressure transmitters or flow meters. Next is what inherent provisions are provided in the design to compensate for the failure. So this is about the design change against the failure mode. Time of FMSA. When is the best time to apply FMSA? Let me repeat my emphasis. All is well that starts well. We usually believe in all is well that ends well. In Korean, 끝이 좋으면 다 좋다. But in system reliability engineering or in designing a complex system, you should keep in mind that all is well that starts well. So the complex system should be designed smart in all the stage. In the later stage, you cannot change the design. What I mean is that the design change you may employ at the later stage cannot fix the problem the system has intrinsically have. These are types of FMSA. There are many ways of FMSA: design FMSA, process FMSA, and system FMSA. Their viewpoint and objectives are slightly different. Design FMSA is carried out to eliminate the failures during equipment design, taking into account all types of failure during the whole lifespan of the equipment. So we can say that this design FMSA is the FMSA we usually refer to. So it is a typical FMSA. Another FMSA is the process FMSA. Is focused on problems stemming from how the equipment is manufactured, maintained, or operated. So process FMSA considered the manufacturing process, not the kind of chemical process. It's about the manufacturing process. Another FMSA, system FMSA, look for potential problems and the bottlenecks in larger process such as entire production lines. So this is a kind of high-level FMSA. So this design FMSA is the typical FMSA we are considering in analyzing a target item or system. There are two ways: bottom-up, top-down FMSA. So as you may expect, as you may guess, bottom-up approach starts with component and rises up, and top-down approach is another way. We see the whole picture first, then we break down the system. I don't know we can distinguish the method clearly, which is the top-down, which is the bottom-up. But typically, I can say that bottom-up FMSA is the typical FMSA we are taking in offshore plant design or any system design. These are standard of FMSA. First is military standard of United States. Second, IEC, International Electrotechnical Commission. It's a kind of international standard. Third one is BS, British standard. Third one is SAE. I guess it's automobile standard. Society of automobile engineers. So it's the FMSA that is applied to cars. So it is not surprising that the car manufacturers are very good at FMSA. Their quality control in many car manufacturers is based on FMSA. Sematech. So there are several standards, but there is no significant difference between these standards. So from now on, I will show the steps of FMSA. There are 5 steps in overall. First, FMSA prerequisite. Second, system structural analysis. Third, doing FMSA. Step 4, team review. Team review the result of FMSA. Fourth, fifth, the last step is corrective actions. That means design change or change in maintenance policy. We should make a decision at the last stage. The first step is prerequisite. That means we need to gather information about the system itself and related information, in short, references. So first step is we need to define the system boundary. And the second is the mission of the system and the functions. So you should keep in mind that failure is about the functional requirement. So we should define the function of the whole system, and then we will define the function of each component, each item. Third one is operational and environmental condition. Second, another thing we need is information. Kind of specific information, so like drawings, specifications, schematics, component list, interface information, functional description, blah, blah, blah. These are about the previous and the similar design, kind of related system. Any new system is similar to some previous ones. So the information about the previous design is very helpful for us to carry out the FMSA. Another thing is interview with the people involved in the previous design. There are many people who has similar experience as our system. So you should talk with the people, the experienced people. Second step is the system structural analysis. So we divide the whole system And the question is, when should we stop dividing the system? For example, we can divide the whole car into several parts: engine, steering wheel, engine, steering wheel, some control system, blah blah. Engine can be divided into pistons, fuel supply system, blah blah blah. And the piston itself can be divided, and the component of the piston can be further divided into each part. So at some point, at some extent, we should stop dividing the component. So the question is, when should we stop dividing the system and the component? So the answer is, what is the manageable unit? What's the meaning of manageable unit? It's about manageable unit is the component unit you are employing in designing or doing maintenance. For example, when the bulb is failed, we replace the bulb with a new one. Then the bulb itself is a manageable unit. We don't have to divide into the valve into socket, filament, glass. If you design the bulb itself, you may purchase the glass, the filament, and the socket. Then, to the design of the valve, the filament is the manageable unit. Can you understand me? When we design a process, a plant, we can buy a pump. Then pump is a manageable unit. If we are maintenance engineer of the pump of the plant, what should we do if the pump failed? If we replace the pump with a new one, the pump is the manageable unit. If we change only the failed part of the pump, the component, the replaceable unit of the pump is the manageable unit. So you should keep in mind that when you stop dividing the system. So this is the kind of example. System is divided into subsystem 1 and 2. Subsystem 1 is divided into subsystem 1.1, subsystem 1.2, blah blah blah. And this subsystem can be broken down. So you should decide this level is proper or this level is proper, or this level is proper. And this is about how to carry out FMSA. Surprisingly, FMSA is a very simple method. So what should we do is to fill in the columns line by line. And let me explain column by column. So each each owner has its own standard sheet. So there can be one more columns, or the title of the column can be changed, can be different, but the overall structure is the same for all FMSA standard. This part is about description of the component, description of the manageable unit, reference number, the number of the component, item description, its function. We know that we should define function to define failure. Operational mode. These three columns is about description of failure. Failure mode, failure cause or mechanism, detection of failure. This column is about effect of failure, consequence of failure on the system, on the subsystem, on the system function. That means it's a partial influence. It's the influence on the whole system, total system. Failure rate ranking, severity ranking, detectability ranking, RPN, risk reducing measures, comments. These are the columns we should fill in. So let me explain column by column in more detail. Reference number, as you may expect, column 1, reference number is a unique reference number to an element, system or subsystem is given. It may be reference to an ID in a specific drawing, or so-called tag number, or the name of the element. So we usually put a number on a component. So it can reduce it can systematically show the where the component belongs. So sometimes we want to, for example, if you have the PNID has a tag number. For example, a temperature indicator can be tagged TT, like this, TE104. Then if we see the tag number, it has a unique number like TE104. So we can interpret that the component is temperature element. One may be some equipment, for example, evaporator. 4 can be serial number. There are several temperature elements. So this temperature element is the fourth one of the several temperature element. So that's the number. That's how we number the component. Second one is about system description. Sometimes this number, this kind of reference number, is not familiar with managers. It can be familiar to engineers, but how about managers? Managers may not have no idea about this number, so you'd better describe the item like valve. But you should put sufficient information like this 2-inch ball valve operated by a hydraulic actuator. So you should put the information like this. You should give sufficient information. Valve is not sufficient. 2-inch ball valve operated by hydraulic actuator is more, gives more information about the valve. Third one is the function. We should define the function. Function of the element or the item. So you should list all the functions. You remember that an item or system may have several functions. So you should give at least all the essential functions of the item. Sometimes the owner side or the standard provide kind of check sheet. So it is a kind of reference sheet. So you can check. For example, valve. If we are dealing with the valve, there can be several functions. Example functions. So we can choose the function. If you have several, if you build up some experience in FMSA, you don't need this kind of checklist. It is good for the beginners. Operational mode. System had several operational mode. Typical operational mode running, operating, but the system should at least another operation mode like standby. Sometimes we should deal with idling operation mode. The component is just waiting to be operated. So if the component has several operating mode, you should deal with all the operating modes. Sometimes some operational mode are not relevant. We don't have to give some considerable consideration on the mode. Then you can skip the operational mode. Failure mode. The potential failure mode have to be identified and listed. A failure mode should be defined as a non-fulfillment of the functional requirement of the functions specified in column 3. So, failure mode, when you define failure mode, you always look at function. Failure mode should failure is defined only if the function is defined. So failure mode is a kind of way of observation of the failure. So the failure mode should be related with the function. Failure mechanism is the true reason of the failure, but it is kind of a guess. We don't know the true reason of failure mode. Failure mode is kind of observation. Failure mechanism is the hidden cause or hidden reason of the failure. So it is kind of just a guess of the failure mode. Detection of failure. Then how to detect the failure. there can be some vibration sensor, temperature sensor, or operator can identify if there is a failure or not. Diagnostic testing, alarms, proof testing, human perception, and the like. You know what human perception is? Hearing, singing. Diagnostic testing is the test to detect the hidden failure. You may remember the classification of failure: hidden failure, detectable failure, undetectable failure. So undetectable failure is sometimes detectable. Why? How? That is the diagnostic testing. For example, the failure with the airbag can be undetectable failure. So the diagnostic testing means we test the airbag directly. I mean head-on collision. This is the extreme case of diagnostic testing. In offshore plant design, we can carry out kind of diagnostic testing by several ways. For example, if we have a gas detectors here, we don't know if the gas detectors are operating well. So, for example, we can release some sample gas. Then we can say that if the gas detector is okay or failed. So you should remember that some failure modes are evident, others are hidden. Operating, if an item is operating mode, it's very clear if the item is failed or not, because it is doing its function. But when the item is in idling or standby operation mode, sometimes it is very hard. It is difficult to identify the failure if the item is operating well or not. This is about the effect of a failure. It's about on the effect on the service system. The second column is about the effect on the whole system. So the effect of the failure of an item can be partial or local, but some failure can be catastrophic or can have impact on the whole system. So doing this, we can recognize which item is critical to the performance of the whole system. Failure rate ranking, severity ranking, detectability ranking is kind of a qualitative estimate. If you carry out kind of reliability analysis, you can detect, you can estimate the precise value of the failure rate or mean time to repair. But when you are doing FMSA, possibly you are not expert of reliability engineering, so you have only a kind of a sense or a magnitude of of the failure rate, failure frequency, or the severity. For example, pump failure rate. How often is a pump failed annually? If you are good at reliability engineering, you can say that most oil pump may have 2 or 3 times failure per year. But even though without those kind of expert judgment, we have kind of feeling in a daily life from our past experience. We have a sense of the failure rate of the pump. If you are a maintenance engineer, you know the rough estimate of the value. So this is about the sense, the magnitude. So usually we define 5 scale, sometimes 10 scale. This shows 10 scale, but from my experience, 10 interval scale is too hard to distinguish. So I usually prefer the 5 range scale. So this is what we are doing. If the failure rate is once per month or more, and if the pump seems to fail every month, then we rank it 5. If the pump fails once per 1,000 years, we rank it 1. Then how can you know? We just live about 100 years. Our professional career is about 10 to 20 years. How can you know the pump may fail once in 1,000 years? So for this kind of judgment, we need a kind of expert judgment about the system. The next, each rank has kind of 10 times. Rank 4, 10 times less frequent. Rank 4 means the pump fails once every year. 3, once per 10 years. So these 3, 4, 5 are the sense we may have from the daily life. This kind of things, rank 4, rank 1, or rank 2, we need expert judgment or spatial information. So usually there is a kind of information sheet. For example, electronic component has a failure rate 1 per 10 to 6 hours. That means once 100 years. So this is the time, the frequency, failure frequency for electronic component. This rank 4 is the failure rate for pumps 1 or 2 times per year. Compressor has higher failure rate, so 4 or 5. How about the valve? Maybe 5. Valve is kind of vibrating actions. the valve stem is moving every second, so it is subject to higher failure frequency. Severity ranking is easier to sense than the failure rate, because now we have we define the failure and then we estimate the impact the impact of the failure. For example, 1 to 3, the rank 1 to 3 is given when the damage is minor. 10, catastrophic, that means several people can be killed. And 4 to 6 is kind of major damage. Detectability. Detectability is about the detection coverage. There is a failure, then what is the probability we can detect the failure? So this is a kind of this is a semantic standard. So 1, 2 is very high probability that if the failure can be detected. So the question is, what is the definition of very high probability? So sometimes it is very hard to define. So frequent way is to set the kind of percentage range. RPN is product risk priority number, is the product of SOD. What is SOD? Failure rate, severity, and detectability. So this column is just product of the 3 columns. 5, 1, 1 means 5 times 1 times 1 is 5. So it's just the product of the 3 columns. Important thing is, the larger the worse. So returning back to the 3 columns, we gave higher value for the higher failure rate. We gave higher severity ranking for the more severe impact, and we gave higher value when the probability of detect is low. So the larger, the worse. So this is very important. When you rank, when you set the rank, you should be careful set the lengths. So if all the these 3 columns are 10 range scales, the RPN, the maximum value of RPN is 10 times 10 times 10, 1000. If you take a 555, the largest RPM is 125, 5 times 5 times 5. Risk reducing measures is the kind of recommendation. What should we do against the failure? So there can be several actions. First is correct the failure, restore the function, prevent the serious concerns. Is the kind of objectives of the reducing measures, but the concrete, substantial reducing measures can be found from failure rate, severity, and detectability. What I mean is that one of your recommendation can be to any way to reduce the failure rate or to reduce the impact of the failure or to improve the detectability. Remarks are kind of some comment are some remarks. They should be recorded for future reference. Sometimes it is hard to reach an agreement. Then some participant of the FMSA meeting want to record something about that. Then we can put some comments for them. So you should remember that this is kind of a simplified summary of the failure. So it can be a cure-all. There can be some missing point, some insufficient explanation. So you can add some remark here. So I think for a simple system, we can spend 2 or 3 days to fill the sheet. Then we complete the sheet, FMSA sheet. Then there is a team to review the sheet. So this is about the team review. So the review team studies the FMSA worksheet and the risk matrix or the risk Pareto number. So we are focused on RPN. What I mean is that RPN is the measure of the ranking of the failure. First, in combination of failure rate, detectability, and the impact. So the larger RPN, the severe the failure, the worse the failure. So we should, for example, we have 1,000 items here. Then the team should review all the 1,000 line by line. No, we should focus on the line with high RPN number. Now you can know the drill, how it works. The team focus on the RPN, high RPN, the item with high RPN numbers. The main objectives of team review is to decide whether or not the system is acceptable. That means there are many items with high RPN number. Then the first question is that should we accept this system design? So this is the first question. There are too many. If there are too many items with high RPN number, that means the system design is bad in an overall sense. Second is to identify feasible improvement of the system to reduce the risk. This is maybe achieved by reduce the frequency, reduce the impact or consequence, or improve the detectability. So system risk analysis and safety engineering seems difficult sometimes, but if you divided the whole system, whole structure into component, sometimes the answer is very simple. If improvements are decided, FMEC worksheet have to be revised and the RPN should be updated. I will show what this means. Problem solving tools like brainstorming, flowchart, Pareto chart, and the normal group technique may be useful during the review process. These are the participants in for the team review. That means all the relevant person should participate in the team review. Project manager, design engineer, test engineer, reliability engineer, quality engineer, maintenance engineer, field service engineer, manufacturing engineer, safety engineer. So it's very challenging job to defend. It's more tougher to defend your thesis. Corrective actions. The sense of corrective actions is very simple. For example, let me give you an example. This is the RPN number we have. It's the initial design. 7, 8, 5. The RPN is just 7 times, 8 times, 5. It gives 280. So if we implemented some action, one is about occurrence, the failure rate. We implemented some countermeasures to reduce the failure rate. Then we can check. We can re-rank the failure rate. So the rank falls from 7 to 5. We have no way to reduce the severity. The severity is the same for the two design, and there is some way to improve the detectability. So detectability comes down by one step. So the revised design is 5 times 8 times 4, means 160. So that's the way we are doing. Make a decision for FMEC. So this is a kind of picture. You should always keep in mind that risk is, what is risk? Frequency times consequence. Don't hesitate. Risk is frequency times consequence. You should not forget this for the rest of your lifetime. So, in order to reduce the risk, there are only two ways. One is to reduce frequency. The other is to reduce consequence. In FMEC, we consider another factor, detectability. So detectability is kind of a third component. So in order to reduce RPN, there are only 3 ways: reduce frequency, reduce consequence, or increase the detectability. The people outside the FMEC think that regard improvement of detectability is kind of frequency mitigation actions. But the people inside FMEC think that the detectability should be separated from the frequency. Pros and cons. Many people love FMEC because FMEC is a very structured and reliable method for evaluating hardware and systems. the concept of applications are easy to learn, even by a novice. So I teach you about FMESA for 1 hour, then you can do FMESA. How many people can carry out FMESA in Korea? Do yes. Not that many, especially in offshore industry. There can be many people in automobile industry, but the number of people who can do FMESA in shipyard are very few. But if you learn the FMESA 1 hour, you can do FMESA. The approach makes evaluating even complex system easy to do. So the concept is very simple. We divide the complex system into part, again, into component, then we carry out the FMESA. We don't know the whole function or problems of the big system, but we know the problems with one component. That's the philosophy of FMESA. There are many cons. FMESA process may be tedious, time consuming. So on Friday, you may know what I mean. The approach is not suitable for multiple failures. So it's kind of straight, cannot handle the variety of failures and functions. It is too easy to forget human errors in the analysis. The majority of the accident is caused by human errors. So we analyze the systems, the hardwares, not the operators. So operators' wrongdoing is not analyzed by FMESA. But as I told you, FMESA survived about 60 years, and it was recognized as one of the most powerful system reliability analysis tool. FMESA, FTA, fault tree analysis, ETA, event tree analysis, and RBD, reliability block diagram, can be the most elementary method for system reliability engineering. For the system analysis, we can add hazard or hazard. So I can say that 6 or 7 methods are the most popular method in system engineering. So we'll learn all the 6 or 7 methods this semester. This Friday, we will carry out FMESA about this system. This system is the LNG fuel gas supply system for large ships. As we know, there is a big trend, mega trend. Something is happening in the shipping industry. Ship propulsion today is based on heavy fuel oil, and it is generating many pollutant materials like SOx, NOx. These days, CO2 is considered as kind of pollutant material. And one surprising fact is that ships are consuming 3% of world energy mix. And but ship is consuming one of the dirtiest fuel in terms of sulfur content. So there are three drivers for LNG shipping. One is regulation on fuel quality. Second is regulation on CO2 emission. These two regulations are already led to implement, will be enforced by IMO, International Maritime Organization. Third one is kind of economic reason. LNG is cheap. So we need a kind of LNG fuel gas supply system for ships. But unfortunately, this is not the real system. There can be some design fault. Personally, I'm doing some project with industrial sectors, so I cannot show the real process diagram to you. So this is kind of example. So, but you should know that this is not the real design. This design is just example. It had some design fault. Anyway, it is a good example for us to exercise the FMEC this Friday. So you'd better to give several minutes to see what this is about. The system is very simple. Here is LNG. LNG is pressurized by pump and vaporized by the heat exchangers and supplied to the engine. Some of the gas should be vented for pressure protection. Since the temperature is around minus 160, this vapor should be heated, warmed up, and this can be used for engine or boilers. This is the overall concept. So we will do the last this Friday. Okay, that's all I prepared for today. Any questions? Yeah.
이거 아까 FMA 워크시트를 통해서 RPM 값을 도출을 한다고 하셨는데요. 그 RPM 값을 이제 그 값이 상회할 경우에 높은 값이 이제 워스트 사항인데 보통 이제 두 번째 12월 리스트 그 랭킹 값이 그 높을 경우에는 그 값을 컬럼은 가중치를 일부 부여하는 게 맞지 않나 그런 생각이 좀 들긴 하는데요. 왜 가중치를 두지 않는 이유가 있는지.
So your opinion is that we needed to put some weight on the severity. You mean the rank itself is a kind of weight. So we don't have any reason to give additional weight on their severity. Another comment I like to add that there is no absolute value, threshold value for RPM. Which RPM we should accept, which RPM we should reject. There's low limit value for the RPM. But each company has its own guideline for the RPM. So the acceptance level is a very difficult question to answer. So we can answer the question about 6 weeks later when we deal with the risk more seriously. Okay, thank you very much.